I guess, are either joint work with or work by my PhD student Mohamed Akhtar, Asya Korti, Sergei Galkin, Vasily Goleschev, Alexander Kapchik, Thomas Prince, and Kaspar Zweiten. Maybe I should start by reminding you what a Fano manifold is. So a smooth manifold, scalar manifold. It's called Fano if and only if the anti-canonical lemma is ample. So this is a positivity condition. And so you can really think of these as kind of building blocks for algebraic geometry. So partly in the sense that they're one of the possible endpoints of the minimal model program. So if you're interested in birational classification of algebraic varieties, then you need to understand Fano manifolds. And partly just in the sense that, most explicit constructions, or many explicit constructions of algebraic geometry start with a Fano manifold. In particular, projective spaces spanning. So that gives you a good head start. Okay, so we know that there are finitely many Fano manifolds in each dimension. So Kalar, Aoka, and Murray. So up to deformation, so finitely many deformation classes.
Is smoothness important there? Is there?
Yeah. So I believe, sorry, I don't know the statement beyond the smooth case. I suspect that if you bound the badness of the singularities in some way, you'll get the same statement. But certainly for smooth ones, there are finitely many up to deformation in every dimension, so it makes sense to try to classify them. So in dimension 1, there's exactly one. So in dimension 2, there are 10 deformation families. These are the Del Pazzo surfaces, known since the 1880s or 1890s. Since before Fano, in fact. So in dimension 3, there are 105 deformation families of smooth Fano manifolds. So this was completed, this classification was completed by Mario Mikai in the 1990s using the theory of extreme arrays. And it's part of Mario's incredible program on the geometry of threefolds. And it builds on the sort of rank 1 classification by Fano and in the 1930s, and by Iskowski. It's hard to spell. I think that's right. Iskowski in the 1970s. And then, so in higher dimension, what about in dimension 4? We have absolutely no idea. The bound that you get out of Kalamia Okamari is very far from type. So what I want to describe is I want to explain a program which is joint work with Korti, Galkin, Goleschev, and Kapchik to find and classify Fano manifolds using mirror symmetry. So the general idea, Fano manifolds are going to correspond under mirror symmetry. I'll be much more precise about this in a minute. To certain very special Laurent polynomials. And as we'll see, so that sort of Fano manifolds up to deformation. And it's going to correspond 1-to-1 with these certain very special families of Laurent polynomials up to an equivalence relation we're going to discuss called mutation.
Can I ask about the dimension 2 case so I understand this?
Yes, yeah.
So if you look at Fano bundles, what are the definition equivalent to
So what would be an example of something?
In the Hertzsprung services.
You want to go into the
So the P1 bundles are, there's P1 cross P1, right? Then there's F1, which is the blow up of P2 in one point. And then the next one is the projectivization of -2 plus O. And that's not Fano, that's only semi-positive. Because it will blow down to P1, 1, 2. Yeah, I mean, it's
0 on the fiber.
yeah. Right, so
the 10 types are the P1 types, P1 and the blowouts.
P2 up to 8.
Points.
Absolutely. Precisely. So maybe we should say that more loudly. The 10 types are indeed P1 cross P1 and the blow up of P2 at up to 9 points. Up to 8 points. Sorry.
0 through 8 is 9 classes plus 1 more.
Okay. So let's say, so what does it mean for a Fano manifold X to correspond to a Laurent polynomial F? I'm going to answer this question twice. I'm going to answer it once from a kind of concrete point of view and once from an abstract point of view, and then you can take which you prefer. Okay, so to begin with the concrete one, so we write down this generating function called the quantum period of X, which is of the form, so it's a power series in this variable t, and it's the sum 1 plus the sum from 2 to infinity of c dt to the d, where cd is a certain Gromov-Witten invariant. So it's the integral over the moduli space of stable maps to X and genus 0 curves with 1 mark points degree d of the d minus 2th power of the cotangent class times the pullback of the point class at one marked point. So you can think, so this is some virtual number of degree d curves in X constrained to pass through a given generic point and with a certain constraint on its complex structure. So it's some Gromov-Witten invariant of X. D here, but sorry, the degree D here, I mean the anti-canonical degree. So if I have a curve C in X, then its degree I'm thinking of as minus kx dotted with C. So I measure, degree is a number here, and it's the degree of the anti-canonical line on your curve. Okay, so that's the quantum period. And we can also form what's called the regularized quantum period, Gx hat, is 1 plus the sum d2 2 to infinity d factorial c dt to d. So if you're familiar with the sort of general theory of quantum cohomology, then you'll know this generating function for genus 0 Gromov-Witten invariance called Gibbenthal's J function. This is the unit. So that's a cohomology valued function. This is the component of Gibbenthal's J function along the identity class in cohomology. Anyway, so it's a generating function for Gromov-Witten invariance. So on the other side of mirror symmetry, you've got this Laurent polynomial f in, let's say, variables x1 through xn. And I can form this thing called the classical period of f, which is, again, a function of one complex variable t, and it's a contour integral, 1 on 2 pi I to the n, times the integral over s1 cross s1 cross s1 n times of 1 on 1 minus tf dx1 on x1, blah, 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 dxn on xn. So actually, I can write this a bit more explicitly. Can you imagine expanding out 1 on 1 minus TF as a geometric series? So then I'm going to get, and then with t to the n, I would get f to the n here in the integrand, right? And then, look, I'm doing an integral over the circle of dx1 and x1. So I'm going to pick the coefficient of x1 to the 0, and the coefficient of x2 to the 0, and blah, 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 and the coefficient of xn to the 0. So bn here is the coefficient of the unit monomial in f to the n. So that's Cauchy's residue.
It's the constant term.
It's the constant term. This is the Laurent polynomial, right?
Yeah.
So it's got positive and negative powers. You take its a big power, but it will still have positive and negative powers, and somewhere in there will be the constant term. So take the constant term.
Yeah. And then this series is called pi f of t.
Pi f of t, indeed. And that that will generally have finite radius of it has finite non-zero radius of convergence. And what we say is that x is mirror to f if and only if the regularized quantum period of x is the classical period of f.
It's just these number of variables n depend on the dimension of the manifold or Fano manifold?
Yeah, so x is going to be an n-dimensional Fano manifold. It's mirrored to a Laurent polynomial.
Okay.
Okay. Let me say this in less concrete terms. Let me say this more abstract. Okay. So the punchline is going to be a certain local system built out of the quantum cohomology of x is going to be equivalent to the Picard-Fuchs local system given by this Laurent polynomial f. So let me say that in more detail. So one thing that you can do with Gromov-Witten invariance is you can build the Dubrovin connection on the tangent bundle to the cohomology of x. So the cohomology of x is just a vector space, so this is a fancy way of saying the cohomology of x across the cohomology of x. And then if I'm at over the point t in the base, then this connection along the direction t to t alpha is d by dt alpha minus the quantum product by phi alpha, where the phi alphas are a basis for the cohomology of x, and t is t1 for t1 plus t. So this is the Dubrovin connection on quantum cohomology of x. The Dubrovin connection normally has a parameter in it called z. I've set z to equal 1.
So t's are coordinates on the...
T's are my coordinates on the cohomology of x, which I'm thinking of as the base. The fibre of this is also the cohomology of x. And this is a flat connection. This connection is flat. That's the WDVV equations. That's the associativity of quantum cohomology. This connection is flat. Okay. And if you remember, my manifold is Fano. So I have my favorite line inside here. So I'm going to restrict to the line which is spanned by minus kf, the anticanonical class, in the base. So then now I've got a flat connection over a one-dimensional base. Restriction of the Dubrovin connection to this. So this is what's called the quantum cohomology local system. On the other side, we have this Laurent polynomial. On the other side, we have a Laurent polynomial, which I want to regard as a map from C star to the n to C. So then I have a local system over C with fibre at T given by the dimensional compactly supported cohomology of the fibre. So now I've got myself a fibre bundle, and that has a Gauss-Manning connection, right? So away from critical values of F, this thing's going to be a fibration. So this homology group has a flat connection, it's Gauss-Manning. So this has Gauss-Manning connection.
You said middle cohomology, so is that n-1 here? And the
Oh,
powers dimension
shoot.
n-1.
Probably. We suppose anyway, it's middle.
Yeah, n-1.
Is that right?
Yeah.
Yes. No, you're right. Sure. Sorry. So that's this Picard-Fuchs local system or Gauss-Manning local system for F. And precisely what it means for X to be mirror to F, in this sense, is that the Gauss-Manning Picard-Fuchs local system for F coincides with the Laplace transform of this quantum cohomology local system. But it's important not to have to say, oh my God, here, because it's not actually that disastrous. So, so how would you get hold of, let's just imagine how you get hold of this, right? So you just take any section here, right? And I differentiate it along with the connection. I'll get another section. And I'll do that again and again. And eventually I'll have 57 sections in a 56-dimensional vector space, right? So in the end, I'll have a linear relation. In the end, I'll have managed to score myself, you know, alpha naught of t times a section plus alpha 1 of t times d of a section plus alpha n of t times dn of a section is 0. I've gotten myself a differential equation. That's the Picard-Fuchs equation, right? And similarly here, you know, I can start with my favorite section, which is probably going to be the constant section 1. I can differentiate it and differentiate and differentiate and differentiate, and eventually I'll get another differential equation. So what I want to do is I want to compare the differential equation there, which is the thing satisfied. So pi f satisfies the Picard-Fuchs equations. That's the connection with what we were saying previously. Mm-hmm. And here, the quantum period satisfies the quantum differential equations. The differential.
The hat is the Laplace transform?
And that hat is the Laplace transform, and all it is, you expand it in a power series, you put d factorials everywhere. Right? That's what the Laplace transform is in this context. So okay, there's some piece of, you know, there's a body of theory, I guess, but in this concretely, that the statement boils down to this. But if you want to think about it more abstractly, it's the Laplace transform with the quantum cohomology local system matching with the Picard-Fuchs local system. Okay.
Why is that more symmetry? So mirror symmetry started off with something about Calabi-Yau threefolds, right? You would expect another manifold on the other side, not a series.
So what happens is not a Laurent polynomial, yeah. Okay. So for Calabi-Yau threefolds, mirror symmetry is something about taking the algebraic geometry of X and comparing it with the complex geometry of the mirror to X. And both X and the mirror to X are manifolds. And if you want to get that working beyond the Calabi-Yau setting, then, so mirror symmetry for Fano manifolds, then again, you're doing about the algebraic geometry of X, but then on the other side, you think about not a space, but a space together with a function on it. It's this thing called the Landau-Ginzburg model. It's an open Calabi-Yau manifold with a function on it. And here,
It would be a torus.
yeah. So if I'm being slight, so yeah, this maybe I want to partially compactify the fibers of this. But in any case, I want an open Calabi-Yau which will contain this as a dense set, and this is my superpotential ion. So, in fact, you can formulate mirror symmetry kind of uniformly as something that goes from spaces to Landau-Ginzburg models, so spaces with open Calabi-Yaus or Calabi-Yau manifolds with functions on them. But in the case where I started with a compact Calabi-Yau manifold, my mirror will also be compact, and then that function is no extra data because it's automatically constant. So you can think of this more general setting as encompassing the Calabi-Yau story as well.
Maybe this is a bit of a digression, but can this be promoted to homological mirror symmetry?
Okay, yeah, absolutely. So I am very hopeful that, so I'm going to write down a bunch of mirrors for Fano manifolds in a minute, right? And I'm going to mirror it in this incredibly weak sense, right? I strongly suspect that what I'm actually writing down, at least if I partially compactify correctly, are homological mirror symmetry mirrors. Okay, so having said what it means for a, so having said what it means for a Fano manifold to be mirror to a Laurent polynomial, in other words, the Laurent polynomial knows the Gromov-Witten invariance of X. That's more or less what it says. So now let's kind of try to answer the question. So what class of Laurent polynomials correspond under mirror symmetry to Fano manifolds? So I have to give you a convincing answer to that, right? Because I've said this is supposed to be a program to classify Fano manifolds using mirror symmetry. So this is the question. Okay. So here is I'm going to give you what was historically our first attempt at answering this question. And at the end, I'm going to give you something which I think is quite a bit better. Something which I think is actually the correct answer to the question. So let's think about trying to find mirrors to three-dimensional Fano manifolds. And these are what are called so what I'm about to describe is the notion of what are called Minkowski polynomials, which were described in joint work with Akhtar and Galkin and Karchak. Okay, so so what I'm going to do is I'm going to give you a family of Laurent polynomials whose Newton polytopes are three-dimensional reflexive polytopes. So, or putting it backwards, given delta three-dimensional and reflexive, what I'm going to find for you is Laurent polynomials f such that the Newton polytope of f is delta. So a reflexive polytope has only the origin as an interior point. All the other, if you think about the lattice points in a reflexive polytope, the origin is the only interior lattice point, and all the rest of them are on the boundary. Okay. So
that's reflexive, is that what you said?
That's not the definition of reflexive, that's a property of reflexive.
Okay.
It's the definition of something called canonical. Okay, but what I'm trying to do is, for each lattice point gamma in delta, choose a coefficient A gamma, And then f is going to be the sum over a gamma x to the gamma. Right, so that's what I'm trying to do. I'm trying to choose a Laurent polynomial whose Newton polytope is delta. So I'm just trying to tell you what these coefficients are. So the only interior lattice point is the origin. So if it's okay, we're going to choose the coefficient of the origin to be 0. So this thing should have no constant. Okay, so now I just need to tell you how to choose coefficients on facets.
Oh, and you had this D starting from 2 in one of your earlier formulas. Yeah, okay.
You should say that again more loudly.
I mean, I was going to ask that question earlier because at some point you put up this generating function that was supposed to pick out the constant term, and you started at d equals 2, and I was wondering why you didn't start with d equals 1.
And that's exactly because of this. And if you looked on the A side, that Gromov-Witten generating function always starts from d. It's 1 plus 0 times t plus something times t squared. So this is just a normalization that's sort of passed to you, that's suggested to you by the Gromov-Witten theory. Okay, so let me tell you how to choose on facets. I want to tell you how to choose coefficients. So if you think about a facet, it's going to be some polygon, right? And it's going to be a polygon in a lattice. Yeah? Because it... So if I see this, I'm going to put 1, 1, 1. And if I see this, I'm going to put 1, 2, 1 on the long side and 1 on the remaining. So these are what are called AN triangles.
Binomial coefficients?
Binomial coefficients. And I'm also going to say, if I see a Minkowski sum, do you remember that the Newton polytope of G times H is the Newton polytope of G, Minkowski sum, the Newton polytope of H. Sorry, the Minkowski sum of polygons is the set P plus Q, where P is in P and Q is in Q. So that's obviously true because think about the possible exponents in G times H. You got them by taking an exponent in G and an exponent in H. Okay, so if I see a Minkowski sum, I'm going to write out the product, Minkowski sums of AN triangles, take the product of the, that's a Laurent polynomial really, just take the product of the facet Laurent polynomials. Also, in my Minkowski sums, I'm allowing myself binomial coefficients on line segments. Okay, recap for a minute. So, I'm trying to write down a family of Laurent polynomials, which are going to be closely related to mirrors for finite manifolds. And how I'm doing it is, you give me a reflexive 3 polytope, and I need to give you the coefficients, right?
Oh, okay.
So now I'm going to decide that the coefficient of the origin is 0, and now I just need to tell you what to do on facets. So on facets, I look at a facet, it's a lattice polytope. I Minkowski decompose it. If it factors into AN triangles and line segments, I know what to do. So let me just do an example of that. So for example, if I ever see this one, if I ever see that lattice polytope, that's equal to the Minkowski sum of the roof and the walls. It's like a house. Right? And this is an A2 triangle, and that's a line segment. So now I would have, so this one would give me, let's see, 1 on x plus 2 plus x plus y. And this one would give me 1 plus y.
How did you know where the origin was?
It doesn't matter, as it turns out.
Oh,
For the coefficient, yeah, it doesn't affect the coefficients. Okay, so then when you work that out, that would be 1, 2, 1, 1, 3, 1, 1. So, something that might not be obvious from what I've said is Minkowski factorization is not unique. So in fact, this house, I could also Minkowski decompose as the left-hand half of the loft plus the right-hand half of the loft. Right? And now I have 1, 1, 1, 1, 1, 1. So this would be 1 plus xy times 1 plus y plus x. And if I write out all of those, I get 1, 2, 1, 1, 2, 1, 1. So this is not a unique prescription. And sometimes I don't know what to do at all. For instance, if I ever see this one, I just don't know what to do. It doesn't Minkowski decompose because it's a triangle. And it's not an AN triangle because it's got an interior lattice point, so I just don't know what to do. In which case I just ignore this reflexive three term and go on to the next one. It's okay, this will get more systematic in a minute.
Okay.
Okay, but now this is a rule, right? So now you give me a reflexive three-toed and I give you a number, possibly 0 or possibly many, of Laurent polynomials that are, I forgot to say something. I always get binomial coefficients on the edges. So I can always stick these facet polynomials together. So now you go when you do that. So there are 4,319 reflexive polytopes up to change of basis. And about 1,000 of those don't support any Minkowski polynomial because they've got one of these faces that I can't handle. But actually, then there are 3,025 where there's at least one. And those together give me 3,747 Minkowski-Laurent polynomials up to change of basis. Up to monomial change of variables.
So do this give you the toric one or something?
No, they really don't. They really don't. So actually all of them. But what's expected to be going on? What's expected to be going on is if x is mirror to f, then the Newton polytope of f is some polytope, and that defines a singular toric variety. And we expect that there's a degeneration from x to the singular toric variety defined by x, by this, the spanning plan of the Newton polytope.
So this polytope can be singular actually. It's not, doesn't have to be smooth.
No, absolutely. I mean, in fact, this would not be, right?
Yeah, that's a singular one.
Yeah. So most of right. But you should think of these as kind of as defining the toric varieties associated to toric degenerations, and you should think of the decorations on the facets as some kind of log structure on the central fiber of this, which tells you how to smooth it out. I mean, that's kind of, I can't make that precise at the moment, right? That's hopes and philosophy and so on, but it seems to be true in practice.
And there's some route or program to improve mirror symmetry based on those log generations?
So I mean, this should plug into the Gross-Siebert program for constructing toric degenerations, absolutely. So they need various pieces of data to get their program running, and one of them is a log structure, and presumably if we think hard enough, we will be able to see a connection between this and what you need to get there.
So on the classics, you no longer have a rectangular lattice. Is that not there?
No, it's okay. It's still a rank 2 lattice, so you just regard it as a lattice polygon in its own lattice.
Can I ask you one thing? I think I know the answer, but so there's not only one degenerate toric varieties.
Wait. Yeah, absolutely. There's not. Can you ask me again in about 4 minutes?
Of course.
He didn't ask you a question, he gave you the answer, and you tried to anticipate the question.
So you're completely right. Okay, so maybe we should set up the question. Okay, so if you're expecting that the reason that a Fano should be mirror to a Laurent polynomial is that there's a toric degeneration to the singular toric variety picked out by the Laurent polynomial, well, there are many different toric degenerations, right? So you should expect many different Laurent polynomial mirrors, yeah? A closely related problem, which is currently on the blackboard, is that I have 3,747 Laurent polynomials, but only 105 Fano manifolds, yeah? So in fact, if you compute the Picard-Fuchs equations for all of these, you end up with 165 families. So there are 160, although there are 3,747 Laurent polynomials, there are only actually 165 Picard-Fuchs local systems, right? So why? So that still isn't 105. I know. Wait. Okay, but why should that? Let's just think about why that should be. So for a moment.
Does that means that the function that you get from
So f and g are distinct, but pi f and pi g, the classical periods, are the same.
Okay.
Right? Just that. Right. So this is this notion. Why should this be true? It's this notion of mutation. So suppose that f is a Laurent polynomial in 3 variables for a minute, but it's going to be very obvious how to generalize this. If I do a GL3Z change of basis, so I do a monomial change of basis, then f will change, right? But by the change of variable formula in the integral, pi f won't change. That's maybe not so interesting because we've already taken care of that by thinking about polytopes up to change of basis, right? So we've already taken care of that. But also I could do something like this. I could go x goes to x, y goes to y, z goes to a of x and y times z, right? And do you remember I'm doing 1 over 1 minus tf dx on x, dy on y, dz on z? That's fine. Because I just scale, dx on x is, I mean, you know, that didn't change. That didn't change. And this, z just got scaled. And that's the invariant. So this change of variables leaves this invariant. So, and most of the time, so let's call this phi. Phi star of f is in general not a Laurent polynomial. Because if you think f is going to be of the form sum from I equals minus m to I equals n of ci of x and y times z to the I, and I want this is, and when I do that change of variables, this is definitely going to be a rational function, but I get a Laurent polynomial if and only if a to the I divides c minus I for all I equals 0. You know, I'm going to have some a's in the denominators here, and they better cancel off, right? But some of the time that happens, right? And so if that does happen, then g equals phi star of f will be a Laurent polynomial. and it's going to have the same classical period as F, right? So now you can check, and that those 3,747 Laurent polynomials fall into 165 mutation equivalence classes. So
Still have to make.
say again?
You still have to make.
Yeah, that's true. That's true.
But does that take care of the ambiguity you have over here?
So
Like with the
So it takes care of this. Sorry, where the ambiguity is. Oh no.
coefficients.
No, actually. So for instance, if you take that, if you take that pentagon and you put it at height -1, and you just cone off at height 1, so you get a pyramid with that as the base. Then there are those two. You can either put a 3 there or a 2 there, and you get two different Laurent polynomials with the same unit polytope. They have a different. Classical period, but as Nathan has shown, this singular type variety smooths in two different ways, and the two different Fanos that you get have the regularized quantum period corresponding to those two things. So it doesn't resolve that ambiguity. That ambiguity is probably just, different Fanos can degenerate to the same type variety. That's life. Okay, so now, in answer to your question about toric degenerations. So there's kind of there's a story here where sort of if we believe the full homological mirror symmetry package, then I give you a Fano variety X, and you should be able to construct a mirror from it as a Laurent polynomial, and the Laurent polynomial the coefficients of the Laurent polynomial should count stable objects of certain sorts in the derived category of X. And then as you change your stability condition, you will get wall crossing formulas, and that Laurent polynomial will change by wall crossing formulas which are precisely these mutations. Right? Or on the mirror side, that would be the statement that, okay, so my Fano manifold should degenerate to a singular toric variety, and you expect that associated with that you should be able to construct a special Lagrangian torus vibration over X. And then the coefficients of the Laurent polynomial will count holomorphic disks ending on that special Lagrangian submanifold, and then wall crossing in the moduli space of special Lagrangian submanifolds both means that your superpotential will change and means that there are other toric degenerations. So that this picture is what you expect. That you shouldn't expect it to be a kind of one-to-one thing. You should expect it to be, Fano manifolds up to deformation going across to Laurent polynomials up to wall crossing formulas. So,
Could you have done a more general mutation here? You could have scaled y by a function of x as well. And
sorry, I somehow didn't say the thing I meant to say. Would it be okay if we then took these and composed them in all possible ways?
and that does it. Okay.
Yeah, sorry. That was what I meant to say.
Got it.
Yeah. So, I mean, which does what you said.
Yeah. Right.
Yeah.
So is A a polynomial there, or what kind of thing is A?
A is a Laurent polynomial. Sorry. Yeah. So these are kind of what you get is these cluster-style birational transformations that preserve this volume form-like thing. Yeah. Okay. So as Jim has pointed out, 165 is not the same as 105. So we still have too many, which is kind of unfortunate. But actually, it turns out not to be so unfortunate, because these 165 things break up in a natural way into two classes. These are what are called ones of manifold type and of orbifold type. So do you remember that? The differential equations that we had on the Fano side came from the quantum cohomology of X, and quantum cohomology of X is graded, and it's got an integer grading, and that tells you something really crude about the structure of that differential equation. Like it's got to have some integers somewhere as opposed to some half integers or third integers or whatever. So now go and look at the Picard-Fuchs operator, and 67 of these look like they're trying to be mirror to orbifolds because the grading, there isn't the integer grading. So this singles out 98 of your 105, and 105 is 98 plus 7, where these 98 have minus kx very ample. And what is true is that these match 1 to 1.
Okay, so in Mori Mukai's classification, 98 and 105 actually have minus k very ample.
Yeah, and they match 1 to 1 with these. They're on polynomials of manifold type. Okay, so that's on the one hand intriguing, and on the other hand, it's kind of this is kind of irritating, right? Because we had too many, and then we threw these things away, and ad hoc way, and now we've got too few. And, yeah. Okay. So here's the second attempt, which I think is actually the correct answer. Oh, and much more seriously, this it's somehow maybe not so clear what to do in higher dimensions, right? That was really a threefold thing, right? Because it was something about the facets. It was a really combinatorial, right? That was all a bit ad hoc. So here's another attempt. So what's called maximally mutable.
So what happened to those 1294 cases where you couldn't assign the coefficients?
So can I come back to that question in just a minute? Because I'm going to give you a better answer which will nail precisely that, and some of these become admissible. Yeah, so we have a better. So this is going to be a better story, and it's not going to give you all of them, because I suspect maybe some reflexive polytopes just don't arise as limits as from toric degenerations to Fano threefolds.
Anything that has that polytope, the example cannot.
Results of Altman, right?
Yes.
Yes, indeed. Indeed, this just doesn't smooth, right? This is if you take the cone over this, you get an affine patch of your toric variety, which is rigid. Like that singularity is rigid. So yeah, so actually, I can't. Right, indeed. Sorry, that's a very good point.
So these two houses, do they have two different smoothings then?
They do have two different smoothings. So if you take the house and you put it at height -1, and then there are two different smoothings. One of which is into the 1,1 hypersurface in P2 cross P2, and the other one smooths to P1 cross P1 cross P1. I can't remember which is the 3 and which is the 2. I don't know whether you can remember. Okay.
So I guess my question was the fact that those two match exactly. What does it say about the leftover cases here? Does it say that none of them are admissible, or does it say that some of them give the same?
So how I want to think of this is that the first attempt here was a very good effort, but it wasn't the right answer to the question. And the second attempt is the right answer to the question, and therefore the ones that don't get hit by the second attempt aren't limits of toric. I can't toric degenerate Fano manifolds to these guys. That's what I want. I mean, so that's a speculation, but I believe that's true. So I think the first attempt was a kind of was a good combinatorial effort, but this I think is better. So can I give you, just in the last 5 minutes, an example of what I mean by maximally mutable Laurent polynomial. And this is going to be a Laurent polynomial which is compatible with as many mutations of the underlying polytope as possible. So let's imagine this, right? So let's seek f such that the Newton polytope of f is delta and the coefficients of vertices are all 1s and f is as mutable as possible.
That's not reflexive.
It's not reflexive. That's one of the nice advantages of this perspective is I can just, so this is indeed not reflexive because otherwise we'd have one interior point. So I can write down the notion of maximal mutable Laurent polynomial makes sense on an arbitrary polytope. Sorry, which means I have a better answer to your question, which I'll get to. Okay, so now, I'm going to put 1s on there. Now, can you imagine the mutation which sends x to x and y to 1 plus x times y? So the origin's here. So everything down here is a coefficient of y inverse. Everything on this line is a coefficient of y to the 0. Everything up there is a coefficient of y. So I'm only going to get a condition. So the condition that we had was only about ai, this thing, dividing this polynomial in x's. So that's got to be divisible by 1 plus x. Actually, it's also got to be divisible by 1 plus x squared, and 1 plus x cubed, and 1 plus x to the 4.
So it forces the binomial coefficients here.
Right. If you don't mind, I'm going to do a change of variables, turn the whole thing upside down, and I'm also going to do that. Okay. Now, let's look at the thing which sends x to 1 plus y times x and y to y. So this is at height, so y is going this way now. The coefficients of y, like that's y to the 0, that's y to the 1, that's y squared. Oh. Right, sorry, coefficient of x, that's okay. Fine. So coefficient of x to the 0,
Yeah.
coefficient of x to the 1, coefficient of x squared. Coefficient of x to the minus 1, coefficient of x to the minus 2. Notice that this thing has to be divisible by 1 plus y squared because of the condition over there. So that had better be a 2. Right? And this has to be divisible by 1 plus y, which nails that as an 8. And then turn it upside down to the same thing again. So now you go look for, so that is what we could call a maximally mutable Laurent polynomial, right? It's as mutable as possible. It supports all the mutations that polytope supports. And it turns out this gives you the Del Pezzo surface of degree 2. So this is mirror to the Del Pezzo surface of degree 2, and there's a degeneration from dp2 to that guy. So you could then, and it's reasonably easy to work out what maximal mutability means in 2 dimensions. It's a tiny bit more subtle in higher dimensions because Minkowski factorization is no longer unique, so you need to say the right thing. But my postdoc Alkapchik and his student Keter Tveitan have solved this problem, and so we have this notion of maximally mutable Laurent polynomials in any dimension. Do you see how imposing maximum mutability gave me a bunch of equations between the coefficients? And what, in this very particular case, those equations had a unique solution. But in general, there will still be some free parameters. So you'll have sort of, so in general, these maximally immutable Laurent polynomials occur in parameterized families. And the ones that don't occur in parameterized families, like this one got nailed completely uniquely, right? So these zero-dimensional families are called rigid maximally immutables. Okay. So now, go classify rigid maximally immutable Laurent polynomials in 2 dimensions. There are 10 mutation equivalence classes.
But the fact that this is not, that there's more than one lattice point in its interior doesn't bother us. It still supports the degeneration from a fan.
Yes.
Okay. Okay.
So, classified in dimension 2, there are 10 mutation equivalence classes. That exactly scores the Delp-Hatzler services for all of them. Now, look at reflexive 3-topes. There are 98 mutation equivalence classes of rigid. No, not, yes, sorry, there are 98, exactly. Mutation equivalence classes of rigid maximally immutable Laurent polynomial. They precisely score the 98. And I know how to find 7 others which don't have reflexive Laurent Newton polytope, and they precisely score my missing 7. I can't actually prove at the moment that there aren't any more, because we have a bit less good control in higher dimension. And then, so now we're off, right? So now, what, 4 folds. So from this perspective, so we're up to about 800 finite 4 folds, about 500 and some which are new. And it's kind of, yeah, but that's maybe.
So these 800 that you found, are they all
They all
ample? As opposed to
yeah.
very ample?
They are all very ample, and they all have rigid maximally immutable Laurent polynomial mirror. Yeah, so there's a And going back to your question about reflexive 3-topes. So now what happens is, you give me a reflexive 3-tope, and I look at the equations that define maximum immutability. And maybe I get a rigid maximally immutable Laurent polynomial, and I do in a bunch of the cases, and that was scoring the 98. But some of the time, it just occurs in a parameterized family. And I believe that what happens at that point is that this is a toric degeneration of a Fano orbifold, and the dimension of the size of the family reflects the size of the orbifold singularities in a precise way. But I actually don't have any examples of that.
Do these numbers give you like a log structure on the toric variety?
We don't know how to do it. So it would be kind of compelling if they did, right? Because you'd want some kind of, maybe not on the toric variety itself, but if you take the spanning fan of and then intersect it with the polytope, you get some polyhedral decomposition of that. So then you'd think of that. So what should be the central fiber of the gross Siebert degeneration will be this thing, and then hopefully you should be able to put logs. The log structure data is then all about the kind of what's the word? The rays. Yeah. And so you'd want. I mean, we're thinking about it. Obviously, I don't have anything.
But do you expect this to be then some kind of Fano in a log sense then? This log variety? If you don't care about the Fano thing, get the toric case somehow in this sense.
I see. That I hadn't thought of it. It seems plausible, right? Because Fano is should be a deformation invariant. Yeah, right, good question.
I have a question that, so does this all, so basically, these decorative polytopes pin down boundary points on a modular space of smooth funnels.
Right.
Does this whole thing tell us something about the geometry of modular spaces of funnel?
Right, so what you, exactly, so good question. So I guess, given that